Hello, everyone, and welcome to the live session for today, September 25th, 2004. My name is Matthew. I am one of the course staff behind the scenes, helping to run these live sessions. We also have online classes, so for those of you who have found us through YouTube, welcome. For those of you who are from our courses, thank you for joining us today. We're happy to be here. Let me go over quickly the way that these live sessions work. Please post your questions in the chat. We curate them, or I curate them from the chat. Please ask your questions only once. If it hasn't been answered or picked, it's because I haven't grabbed it yet. It's not because I haven't seen it. We try to get to as many questions as possible. We also try to give as many people an opportunity to ask questions as possible, and we try to cover a variety of topics. We keep this at a beginner level, so if you have advanced mathematics questions, we may not choose those. So with that being said, go ahead and post your questions in the chat, or you can send them via email, which I posted in the chat. You may have to scroll up a little bit if that's more comfortable for you. And Chris, why don't you go ahead and welcome everyone, and then we'll get started with questions. Actually, you can give us a quick overview of some interesting astronomy research that's current, and then we can get started with questions from the chat.
Yeah, sure. Welcome everyone, however you encountered us. And before I start taking on questions of astronomy, I thought I'd comment on a news story that was on several outlets. Probably Scientific American is where most people might have seen it. So it's a question of miniature black holes or micro black holes, and whether they might account for what astronomers have been looking for half a century, which is dark matter. So the backstory is that, I'm not without going into detail on dark matter, we get questions about that almost every week. Astronomers and physicists in particular have not succeeded in identifying dark matter. It's presumed to be a fundamental particle because other things have been ruled out. But the Large Hadron Collider has been testing the standard model of particle physics for things that are not in the standard model. It could be the dark matter particle, and has come up dry for several years. It's a very big disappointment for high-energy physicists. It's also a disappointment for cosmologists because it's not clear that the subatomic particle they've been thinking of and looking for is the dark matter. And that's opening the door to more interesting and unusual, maybe less likely possibilities. One possibility for dark matter is microscopic black holes. So we know there are stellar mass black holes, dead stars that collapse in their cores, and we know there are massive black holes in the center of every galaxy. But in the early universe, just after the Big Bang, conditions were so intense that tiny black holes could form. Many would evaporate before the present day, over billions of years, according to Hawking radiation, but some might not, and they might still be in the universe as the dark matter. And this method involves looking for these tiny black holes, which are of course invisible, they're dark, but they do deflect light, and they distort the way matter moves around them. And so there are clever ideas for how to possibly find micro black holes, and it could still be possibly the dark matter, but the jury is out on that. Okay, ready for your questions on astronomy.
Excellent, thank you very much. Sorry, my computer is being a little slow, so if there's a pause, that's because my system is being a little herky-jerky today. The first question, which came in before the black holes discussion, is actually about black holes. Terrence would like to know, black holes are the foundation for a stable galaxy as observed in our very own Milky Way. Is it possible to say that we live in a black hole?
I think that would be pushing it. It's important to remember that although galaxies do house black holes, the black holes on average are 0.1% or less of the total mass of the galaxy. So they really are quite a tiny component of the galaxy, most of which is stars and dark matter. Milky Way is an example, 4 million solar mass black hole, and the mass of the galaxy is, hundreds of billions of times the mass of the sun. So the black holes in the center of galaxies are maybe large for a black hole, event horizon the size of a solar system, but that's still a tiny region of space. So relative to an enormous galaxy, they're small, and they're a small percentage of the mass, so they don't dominate.
The next question is from Adrian, who's on with us live. What will the universe look like one day, 1 hour, 1 minute, and 1 second before it were to collapse back into a black hole?
Well, it's unlikely that will actually be the outcome. The current measurements suggest that the accelerating expansion will continue. We don't know that that will be true forever, because there's a very active debate in the research community about whether dark energy is constant over space and time. There's indications in some large recent surveys that dark energy may not be a constant. Now, if dark energy does vary over time, it's possible that it could decline to the level where the universe could recollapse. And so indeed that is a possibility for the universe. But based on current measurements, it looks like the expansion will continue forever. If the universe were to recollapse, it would indeed approximate a black hole in the final event, like a singularity, and the matter would be rushing in towards itself, and the space-time would be folding in on itself at essentially the speed of light.
The next question is from Hamed, who asks, is there going to be a comet visible? I've heard about this too. In fact, I've seen some folks taking pictures of it on my Facebook page. Can you talk about whether it's going to be more visible, or what we're seeing right now?
Yeah, this comet, I've only seen one article about it. It's always very unclear how bright any new, especially a newly discovered comet is, in any particular approach to the Earth. Halley's Comet is a good example. That's a very periodic 76-year orbit comet that's appeared on Earth dozens of times, and it's very different in brightness from one orbit to another. So it's very hard, I think it's hard to tell whether this is going to be a binocular object, a small telescope object, or a naked eye object. But it seems like it's a small comet not coming that close to the Earth, so it probably will be binoculars or small telescope to see it.
The next question is from one of our live participants. Dan Cooper asks, can you elaborate or talk a little bit about more about the new tiny moon that will shortly be orbiting the Earth?
Right. So the Earth is possibly going to capture a small object that will turn it into a little moon or a moonlet. I mean, it is truly tiny. I mean, millions and millions of times smaller than the Earth's moon. And that's not an unusual circumstance. Planets, there's a lot of interplanetary debris, and if that approaches at a slow net velocity to the Earth's orbit, then it can be gravitationally captured and turned into a tiny little moon. But again, this is a very small object, not be visible to the naked eye. But it's interesting that planets can capture objects from time to time. It's not clear how long-lived or stable that little moon, that tiny moon, will be. I don't think the calculations have indicated yet.
The next question is from Stanley, who sent an email. In a UA Now story on the Hubble tension debate, it talks about the tip of the red giant branch. It mentioned that when a red giant starts to ignite helium, its temperature and brightness drops. Since it takes more energy to fuse helium, why does the temperature and brightness of the star drop?
Because the star reconfigures to a new situation. So in advanced stages of stellar evolution, the star structurally almost bifurcates. There's often an outer envelope that is very detached from what's happening in the core, and that's true with the red giant. With the red giant, there's a cool outer envelope, and to the outside observer, that's why it looks red, because the temperature of that envelope is only 5, 6, 7,000 Kelvin. But meanwhile, in the interior, gravity is forcing the core, having exhausted one nuclear fuel, to collapse to a new higher temperature. And so it's that bifurcation of a outer cool envelope and a interior hotter, denser situation that leads to this situation for a red giant.
Ragnar Lodbrok, who's on with us live, would like to know if there are any new online astronomy courses that are coming up or in the works.
Not from us, and this world of online courses is so big now that I don't essentially know how to keep up with it. So there are MOOCs and online astronomy courses being launched all the time. I have a slight notion to turn the book that I'm working on right now, which is about cosmic chemistry, into a little MOOC. Probably not as long as our main astronomy MOOC, maybe half the length of that, but that wouldn't be till next year.
Excellent, thank you. The next question is from, let's see, from Sphere, who asks, can you talk a little bit about chemosynthesis, but they want to know if chemosynthesis in Earth's ocean is feasible.
I'm not quite sure what that term means in this context, so I don't think I can answer that unless I have a definition.
Yeah, no, I understand. That's fine. The next question is from, so Sphere, if you'd like to clarify that question on the chat, I can re-ask it. The next question is from Arif, who asks, why do astrophysicists divide critical mass of the universe by the Hubble radius for various universe models?
That's a way of distinguishing the world models or the different outcomes of the universe. Because the Hubble radius is sort of the scale of the universe. And so you want to normalize whatever you're talking about by the current scale of the universe, because it's the density of matter and energy in the universe at any particular size that determines whether it'll expand forever or recollapse.
The next question is from Neha Bagelu, who asks, how can astronomy help to solve sustainable development goals?
Well, astronomy is mostly looking outward. It's mostly a research activity, so it's not intricately connected with sustainable goals, but it has a role in sustainability because, of course, as a science, it's important for us to know what our footprint of our science is. If science disrupts human activity, uses resources or energy, or worse still, emits a lot of carbon footprint, then that's a bad situation. So sustainable astronomy essentially means astronomy that doesn't damage the environment, doesn't lead to any exacerbation of climate change, doesn't make the night sky, which is a precious resource for the entire world, make it any brighter in either radio or optical senses. And sustainable astronomy also means making it sustainable where it's a part of everyone's culture. So spreading it so that it's not just a small cadre of people in rich developed countries who are doing the astronomy.
The next question is from one of our online participants. Is there a possibility of existence of white holes and or wormholes?
Well, white holes and wormholes are theoretical constructs that do not violate general relativity. In other words, they're allowed by our best theory of gravity. But there's no experimental indication that they exist in the real universe. So they're theoretical, mathematical constructs. Wormhole is an interconnection between different disparate places in space-time. And a white hole is possibly the counterpart to a black hole, where the matter and energy that disappear into a black hole emerges again in some disparate part of space-time. Our universe seems to be quite uninteresting topologically. In other words, it's geometrically flat. That's been measured now for decades. And so there's no indication of interconnectedness of our universe, which would be required for both a wormhole or a black hole or a white hole.
The next question is from an email. Wendy asks, is radiation the primary reason that the Clipper won't land on Europa, and why it will end its mission on Ganymede rather than returning to Earth?
Yeah, the Europa Clipper, which is a very exciting mission by the European Space Agency with some NASA involvement, of course, is very exciting. But Jupiter has an intense magnetic field, and it's a very extreme radiation environment. So any mission to study the giant moons of Jupiter is entering very difficult terrain. Now, we've had missions to Jupiter in the 1970s and 80s, so we've measured the radiation, and we know that there was some radiation damage. And what happened recently was it was determined that some of the electronic components in the instrumentation of the Europa Clipper were not sturdy enough or hardened enough to survive what is likely to be the radiation environment that it finds there. They seem to have papered this over or fixed it. I'm not quite sure if I'm convinced that they've totally fixed it. The mission will go ahead. And that extreme radiation environment is definitely a big challenge to any long-term study of the moon. And so that Clipper mission is not spending all of its time in Europa, which is the most intense part of the radiation environment, and will explore other parts of the Jovian system.
The next question is from Pecorin, who's on with us live. Do interstellar planets exist?
Yes, it's almost certain they do. We've got some indications they do. The reason they are thought to exist, both theoretically and observationally, is that solar systems are unstable in their early phases, and sometimes even in their late phases. And those instabilities, those orbital instabilities, can lead to the ejection of one or more planets, usually soon after the formation. And those ejection velocities are sufficient that those planets leave the system and travel through interstellar space. So they are unattached to a star. So that's been expected theoretically, and simulations confirm that that should happen. And now we have some indications through lensing experiments that free-floating planets do exist. They're not very strong observations yet. It's a very difficult observation. By some calculations, there might be not quite as many, but a good fraction as many free-floating planets as there are planets tethered to their stars.
The next question is from one of our live participants, is from an email from Ravi, who asks, the WMAP and Planck satellites gave us maps of temperature fluctuations, which led to density fluctuations in the young universe. If we look today at the areas of higher density, would we see galaxies, clusters of galaxies, or other large structures? And if so, do astronomers use those WMAP and Planck satellites to find interesting regions to point their telescopes?
Yeah, that's a good question. So with the study of the microwave background through those two missions, you're looking at the universe as it was about 400,000 years after the Big Bang. And so those very small temperature variations indicated by microwaves are indeed places where the density is slightly higher and slightly lower, and we can project that forward to a situation where there should be objects much later at those directions in those positions. The trouble is these are very small fluctuations. They're 1 part in 100,000. And so it's very hard to predict what kind of structure will actually form hundreds of millions of years later. And that's because the growth phase observed in microwaves is a linear growth phase, and that's very simple to model. But as soon as the density gets higher, it's a nonlinear process, and that is almost by definition a hard process to calculate and predict. So no, there's no direct one-to-one mapping between a hot spot or a cold spot in the microwave background and a present or near universe large-scale structure.
Kat Randall, who's on with us live, would like to know, what is your favorite area of astronomy research currently?
Well, I have been doing cosmology, observational cosmology, for a long time, and that's still a very hot field. Witnessed the discussion recently about dark matter and micro black holes and dark energy and whether it's changing over time and so on. So these two big ciphers of cosmology, dark energy and dark matter, are still subject of intense investigation, theoretical and observational interest. So that continues to be my favorite subject. And a close second, of course, are exoplanet research, because the diversity of exoplanets being found is really amazing.
The next question is from one of our live participants. Krishnarajan asks, how does an object that's captured affect its host's rotation?
Well, there's coupling between an object that's in a captive orbit. So there's the gravitational connection between the two is an equal and opposite force according to Newton, but that coupling leads to a tidal force. So there's a differential gravity between the larger object in the front and the backside of the more distant object, and that's a tidal stretching force. that same tidal interaction also can cause locking, where when the orbiting object is relatively nearby and relatively small compared to the major object, then it will tidally lock, leaving one face always pointing to the larger object, and our moon is the example of that. We always see the same face of the moon. And so this coupling, this transfer of energy and angular momentum also usually leads to a slow change where the object that's in what amounts to a stable orbit will gradually recede, move to further away, and the conservation of angular momentum then indicates that the primary object, say the Earth, if it's the Earth-Moon system, will start to spin slightly slower, and we've observed both of those things.
The next question is from Terrence, who has a question about solar winds. And I'm just going to simplify the question, Terrence. Hopefully I'm getting the gist of it. But can you talk a little bit about where do solar winds come from? How are they generated? How do they, come towards Earth? Or do they, do these winds somehow get in orbit around the sun, like the Earth orbits the sun? Can you talk a little bit about their generation and effects?
So solar wind, and in that phrase it refers to the sun, but other stars, essentially all stars, have some kind of a wind. What that means is that the outer part of a star is an intense radiation environment. For instance, the chromosphere of the sun, which is beyond the sun's visible surface, is extremely high energy and a temperature of 1 million or 2 million Kelvin, emitting a lot of X-rays. And so it's acting like a particle accelerator. So the outer environment of a normal solar type star is accelerating particles and also emitting high energy radiation from that hot region. And that radiation travels to the planets like the Earth, and those particles travel at not quite light speed but at very high speeds also towards the Earth, and that combination of radiation and particles is the solar wind. In the Earth-Sun situation, it interacts strongly with the magnetic field of the Earth. It creates weather on the Earth, it creates space weather, it creates the aurora when those particles funnel in along the magnetic poles and excite oxygen and carbon and nitrogen atoms in the atmosphere. So there's a lot of effects from the solar wind.
The next question is from Neha Begelu, who has a general question about, can you talk a little bit about radio astronomy? So I'll just embellish, what's it good for? What do we see with radio astronomy? Where did it come from? How do we get this idea?
I'll give a condensed answer because it's a big question, but a good question. So radio astronomy is a foundational part of modern astronomy. It's essentially looking at the low energy universe, because radio waves have low energy and long wavelength and low frequency compared to visible light. So radio observations typically look at low temperature and low energy phenomena in the universe, but not exclusively, because particles can be accelerated that also emit radio waves. Radio astronomy started in the 1930s with the first development of radios. Of course, radios were invented earlier than that, and they soon went into astronomers' hands. The first telescope was built by Grote Reber, I think in 1934, and for a long time, maybe a decade, he was the only radio astronomer anywhere. Karl Jansky came along thereafter, and some Australian radio astronomers in the 1940s. But radio astronomy did not really take off until the 1960s, when radio receiver technology matured. Some large radio telescopes were built for the first time, and now it's a part of modern astronomy because there are dozens of radio telescopes around the world. The niche that radio astronomy occupies that's very hard for optical astronomers to simulate is combining separate radio telescopes to effectively act like one huge radio telescope. It's called interferometry. And radio interferometry has been going for decades, and it's a very powerful way of getting extremely sharp, high-resolution radio images of the universe.
The next question is from Judith Tavano, who asks, what is the latest on the T Corona Borealis nova? It seems to not have exploded or erupted yet. Can you talk a little bit about what that is, what's expected, and what's going to happen.
I'm going to have to punt on this one because I've not been keeping up with that story. I know what the nova is, but I'm not current on it.
Okay, yeah. Other than that, I mean, I just Googled it and it hasn't erupted yet. So we'll, if it happens, then we'll certainly talk about it on stream. The next question is from one of our live participants. Maria asks, is Earth, along with the solar system and Milky Way, moving through the universe? If so, how does this movement relate to the larger structure of the universe and the expansion of space?
Yes, the Earth and the Sun are in a net motion with respect to the universe as a whole. The universe as a whole, the reference frame for motion is defined by the microwave background, because those microwaves permeate space and they're not going anywhere because they're the whole universe. So we measure motions with respect to the microwaves of the Big Bang, which we can detect easily with radio telescopes. And relative to that radiation, the Earth is, of course, orbiting the Sun. The Sun is moving around the Milky Way galaxy, and we measure both of those motions. The Milky Way galaxy is falling towards M31, and both of those galaxies are slowly falling towards the Virgo cluster, a large group of galaxies, and we can measure those motions too. The Virgo cluster also has a net motion relative to a supercluster of galaxies called the local supercluster. And then when we get to that scale of hundreds of millions of light years, we do reach a reference frame which is inertial, in other words, which represents zero motion with respect to the universe itself. So on all scales up to about 100 million light years, we see net motions and we can measure them.
Excellent. Thank you very much. The next question is from one of our live participants. Diana asks, what are the main future ambitions of astronomy in terms of discovery and development of new theories? Basically, what's new in the future for astronomy, and what are researchers looking forward to and working on now?
So astronomy is driven by now big surveys, typically survey telescopes. That's how cosmology is being driven for sure. And so we're on the edge of some very big surveys. What used to be the Large Synoptic Survey Telescope, which is now the Vera Rubin Observatory as it's named, down in Chile, is going to start doing an all southern sky survey in a year or so with a 6.5 meter telescope. The mirror was made here at the University of Arizona and the secondary. That's a very powerful survey, looking at things that change from one night to the next or 1 week to the next. There's also the Roman Space Telescope, which is on the drawing board and will be a successor in a sense to the James Webb and the Hubble, and that's a very powerful survey telescope. So those are two surveys that astronomers are looking forward to. Radio astronomers have their own plans for a replacement for the Very Large Array, which will increase its sensitivity. And radio astronomers also have the Square Kilometer Array, which is an international project that will improve the sensitivity of the deepest radio observations by a factor of 100. So there's a lot of anticipation of that. The field that's sort of left out in the cold by all this is X-ray astronomy, because as you've probably seen, the Chandra Observatory, one of NASA's great observatories, is, in its waning years, still very effective and really still the only X-ray observatory. Those observations have to be done from space. And NASA is essentially going to pull the plug on it at the current moment. But there's a huge activist campaign among astronomers to keep going with Chandra, otherwise we'll lose a very important X-ray window on the universe.
Can you talk a little bit more about Chandra, and is it one of those situations where the telescope has run out of coolant, or is it just that they don't want to, is it simply a funding issue? Is it losing sensitivity?
Right. So why is Chandra on the chopping block? It is a combination of things. It is a little bit sensitivity issue, and it's more importantly, I think, funding. So the sensitivity is such that in an older facility in its third decade, detector arrays degrade over time. So Chandra has a certain frequency range or wavelength range of sensitivity, and the degradation in some of its detectors is causing it to lose the low end of that frequency range. That still gives it a large frequency range, including many important X-ray transitions spectroscopically, and an important energy regime for studying the universe. But there's some degradation, but it's not dramatic. It's in the margins. The cost issue is substantial because as telescopes age, their running costs don't really go down much. There's a marching army of observers and technicians and staff required to keep the observatory running, to service the people who use the telescope with data and help them reduce and calibrate it. And so NASA keeps accumulating costs when observatories continue and then new ones are built, like James Webb. So something usually has to give, and it's typical that they'll want to downgrade or deorbit or cut off funding for the oldest facility that they're supporting, and that's unfortunately the situation Chandra ended up in. The people behind Chandra and the people who use it, and even people who are not X-ray astronomers, are trying to argue that the cost saving there in NASA's $18 billion a year budget would really be quite marginal, and it's a false economy to pull a plug on a very productive facility, because that's been demonstrated.
The next question is from Astro Taha, who's on with us live. There are multiple recent news articles about the, quote, crisis in cosmology, and that it could mean we are on the verge of discovering new physics. What are your views on this?
The crisis in cosmology has been brewing and bubbling for a few years now, and I keep up with it. It's not clear how this is going to resolve. The Hubble tension controversy, which is the difference in the measurements of the local expansion rate of the universe, the local Hubble constant, and the expansion rate inferred from observations of the microwave background in the early universe. They should agree with each other in the standard expanding universe model. They don't. And that disagreement hasn't really gone away. But people have recently identified possible systematic errors in the way the local Hubble constant measurements are done, and that could alleviate the discrepancy and maybe make it go away. So people who are cautious are just suspending their judgment on that. They don't know that the Hubble tension is real. The other crisis, of course, is the fact that we haven't been able to identify what dark matter is, and the fact that the high-energy physics world is not showing evidence of any new physics that could explain dark matter. So that's a crisis in physics as well as a crisis in cosmology, and that's not gone away, and it's getting more acute actually as time goes by, because physics experiments are gradually closing the window on a plausible subatomic particle candidate for the dark matter, and that will leave not much else, and then you may be in a crisis as people are talking about it. But again, too early to call crisis. These articles appear almost monthly, but most calm observers just say, well, we got to wait a bit, and often people underestimate their systematic errors, and these are very difficult observations, so it pays to take a slightly long view of that.
The next question is from Dennis, who's on with us live. Can you please comment on the future of land-based telescope observations with regards to the increase of small communications satellites going into orbit?
Yeah, the small satellite problem for astronomy is quite significant. The constellation of satellites, which are tens of thousands of satellites. SpaceX is the biggest launcher of mini satellites, but there are others, and the total number is projected to almost hit 100,000 by the end of this decade. These have now two problems. They obviously glint a lot of reflected light, especially when they're down near the horizon, near sunrise and sunset, into big optical telescopes, and they spoil an increasing number of the images from a deep optical survey, something like 7 or 10% now, and that number will grow. Radio astronomers are upset because the telecommunications capability of these satellites occurs at frequencies that radio astronomers use. And so tens of thousands of these satellites is going to create a radio din that may make it very hard to do certain radio observations. So both of these are issues of real concern for astronomers right now, and they're not getting any better because the number of players and the number of satellites projected to launch just keeps increasing.
The next question is from Mohammad, who asks, is there supposed to be more lithium in the universe, and why isn't it as abundant as hydrogen and helium?
So lithium is a light element, and it is produced in the Big Bang, and it's produced at a very low level because the Big Bang, of course, only was hot enough to do nucleosynthesis, to create elements beyond hydrogen, the simplest element, for about 3 minutes, basically. And so it makes a very small amount of lithium, so it's a tiny fraction of the amount of hydrogen. There's disagreement as to whether the amount of lithium observed is in agreement with the Big Bang or not, and that's because lithium is created and destroyed in certain types of stars. And so it's hard to extricate from the cosmic lithium measurement which of that lithium came from the Big Bang and which of it has subsequently been created or destroyed in stars.
The next question is from one of our live participants. Neha asks, what are fast radio bursts?
So there are a set of radio burst objects. These typically are collapsed stellar objects which have jets or high energy radiation in their outer envelopes, and they represent often the debris from a cataclysmic explosion. The fast radio bursts last a fraction of a second and then they go away, and they represent probably the formation of a compact object. Monitoring them or understanding them is difficult because the signature of the burst is made at radio wavelengths, but to physically understand them you'd also need optical observations, and it's really hard to get both radio and optical observations of a fast radio burst.
The next question is from one of our live participants. Astro Taha asks, are there new astronomy fields or observation techniques on the horizon? Sort of like gravitational wave astronomy, gave us a new window onto the universe. Is there anything else coming up in the future?
Yeah, gravitational wave astronomy, it was new. The first detections were less than a decade ago, and it's growing rapidly with more detectors and more instruments planned. A field that's been around for a while but is having a maturation and emergence recently is neutrino astronomy. So neutrinos are very elusive subatomic particles. They interact very weakly with matter. They have no electromagnetic interactions, so they're hard to detect. And the first neutrinos were detected actually from the sun decades ago, and the first neutrinos from beyond the Milky Way were detected less than a decade ago. So neutrino astronomy is a field that's real and it exists, but it's still in its infancy. So we could probably expect to see the biggest growth in neutrino astronomy in the next decade.
The next question is from one of our live participants. Pecorin asks, what would happen if two neutron stars collide? Would it just create a black hole?
If two neutron stars collided, indeed it would create a black hole, because neutron stars are below the mass required to create the situation of a black hole, an event horizon and a Schwarzschild radius. But if you combine two of them, you put yourself over the top and make a black hole. More dramatically, colliding neutron stars are now thought to have caused the creation of most of the precious and heavy elements in the universe. In other words, a majority of the gold, silver, platinum, and even heavier elements comes from colliding neutron stars. And that's because in the collision, the neutrons, which have no electrical force because they're neutral, can merge, be crushed together, and with neutron decay, one will turn into a proton, and so you ratchet up the atomic number and you can generate heavy elements very efficiently. And models and simulations suggest that neutron star collisions really did create most of the gold in the universe.
The next question is from an email. Wendy asks, can you explain how a gravity assist works and why a spacecraft might, for example, come to Earth and then go to another planet and then seemingly come past Earth again on its way to, say, the outer solar system or to Jupiter? Like, why might we take this long route that seems to be kind of going back and forth between two planets?
Right. Gravitational assists have been used by NASA since the 1970s, really since the first space probes were sent into the outer solar system. So to get to the outer solar system against the sun's gravity, you need to attain some pretty high speed, not just the speed that got you off the Earth, but a much higher velocity. And to get that higher velocity, you either will use rocket fuel, which means the mission is expensive and heavy, and that often is not feasible, and you still go very slowly, or you use the trick of gravitational assist. So gravitational assist is just a very simple physics where if you have a small mass object approaching a large mass object, you can use conservation of energy and angular momentum to give a very slight amount of the large object's angular momentum and energy to the small object and accelerate it. Because a satellite that goes around a planet is tiny compared to the mass of the planet, the loss of energy and speed of the planet is undetectable. I mean, it's tiny. So it's almost like you're getting it for free. And so the method used to get into the outer solar system for 50 years now is to take the satellite and counterintuitively send it typically towards Venus, a twin of the Earth, so quite massive, and do a gravitational assist around, swing it around Venus a couple of times, and then it kicks out into the outer solar system. And it goes with a much higher speed to the outer solar system than it would have if you just sent it off the Earth straight there. Gravitational assists can get quite complicated. There are gravitational assists that have been done around multiple planets. The outer solar system missions like Cassini use gravitational assists to navigate around the outer planet systems to get stable orbits around some of the moons to study them. So it's a very sophisticated method of orbital mechanics that NASA engineers have perfected, and it's quite impressive. And otherwise we really couldn't explore the outer solar system.
The next question is from one of our live participants. Hamed asks, has anyone hypothesized a connection between dark matter and dark energy?
People talk about this, and it's almost a natural thing to do when you have two big unknowns in a subject. You might want to connect them and kill two birds with one stone and solve the problem with one idea. In practice, though, that has resisted any reasonable physical attempt to do that. And that's because dark matter and dark energy manifest in such different ways. Dark matter manifests as a mass component of the universe that binds galaxies and creates some of the large-scale structure in the universe, whereas dark energy is imputed to space-time itself and is causing the accelerating expansion of space-time. Those are very different things, and so there's no plausible physical explanation at the moment that could unify those two unknown entities.
Next question is from the Creador channel, who asks, they ask about black hole blasts, but I'm going to specifically I'm going to change this to just be about black holes because that's what it seems to be about. You can correct me in the chat if I'm wrong. Can you please explain how black holes form when they were discovered and what negative impacts they might have on us or anything else?
Black holes of the classical kind, which are collapsed stars, form when a star reaches the end of its life, a massive star. And after the end of the exhaustion of all the nuclear fuels, if the core is more than about 3.5 times the mass of the sun, as it collapses under its own gravity with no new energy or pressure support from fusion, you have the definition of a black hole. So that was a prediction made in the 1940s and 50s. The first black hole was not detected or observed until 1969. It was Cygnus X1, the brightest X-ray source in the constellation of Cygnus, which is a binary star system where there's a blue supergiant orbiting a black hole. And within a year of those first observations, it was pretty clear that that was a real black hole. And since then, dozens have been found with similar quality data, and it projects to maybe 30 million small black holes around the galaxy. Large black holes were discovered in a different way and later in the 1960s and 70s, and we now know that they exist in every galaxy. Black holes are pretty remote because they're very unlikely objects. The one in our galaxy is 27,000 light years away, and black holes form from the most massive stars, which are rare. So the nearest black hole is several hundred light years from the Earth, so they're not really anything we need to worry about.
The next question is from Terrence, who's on with us live, who would like to know Sorry. Is Betelgeuse, the star Betelgeuse, going to implode anytime soon?
I mean, it will eventually. It's a red supergiant, and so it's a massive star, which when it exhausts all of its nuclear fuels will undoubtedly have a supernova explosion and collapse to form a black hole. But it's not clear that that's going to happen anytime soon. We are not sufficiently precise in our observations of any individual star to put a particular timing on these very rapid, dramatic ending points of a star's life. So we can just flag stars as saying this is how we think they will die, and maybe it will happen in 100,000 years or 1,000,000 years or 10 million years. It's really that uncertain.
Excellent. So the Creador channel specifically would like to know about, so when I'm going to guess they mean, because black holes themselves do not explode from my understanding, but the explosion or the event that forms a black hole, are those, I guess, what are the results of those explosions or those stellar, I don't know, formations or these combination events, those kinds of things? Are they dangerous to anything nearby or to us? Like, what are the threats to Earth?
So a black hole does form as a result, as a byproduct of an explosion, which is a supernova explosion, the detonation of a massive star. As it collapses, creates a blast wave going outward, forming heavy elements, high energy radiation, intense light, brightening by a factor of billions, while inside the pressure of gravity is forming a black hole. If that process, that supernova explosion and black hole formation, happened within, say, 10 light years of the Earth, that would be a problem, because the radiation from the supernova would be very damaging to the Earth's ozone layer and eventually the biosphere. But there are no black holes near the already existing that close, and there are no objects likely to turn into black holes that close. So the danger of black holes to us is just not a real danger because they're so far away.
Sunit would like to know if it's possible that black holes could just be factories for dark matter.
That has been suggested, that the black holes contain dark matter. It doesn't solve the dark matter problem, however, because again, black holes are rare. They're concentrated objects, and even if they contain dark matter, the net amount of mass of dark matter in all the black holes in the universe, assuming they all had dark matter in them, would not be enough to explain the behavior of the universe, because the dark matter in the universe is more dominant than normal matter by a factor of 5 or 6. So even if there is some possible dark matter associated with black holes, it's inadequate to explain the way the universe works.
Excellent. The next question is from an email. Dave McKenzie would like to know if there is a date when the Habitable Worlds Observatory will be ready, and how will it complement other telescopes already searching for exoplanets?
Habitable Worlds Observatory, HWO, is a NASA mission, very exciting one that's designed to follow up all the work that's been done by the surveys like Kepler of discovering exoplanets, to home in on the most habitable exoplanets and characterize them and detect life in them, to really not just understand if they're habitable, which we know for hundreds of exoplanets, but to see if that habitability has led to microbial life. So it's a very ambitious space mission. It has a star shade, has very high resolution imaging and spectroscopy, and the launch date is very uncertain because NASA's budget is so constrained. Having talked about if NASA's budget is constrained to the point where they might cancel the Chandra Observatory, we're still dealing with the big cost overhang of the James Webb Space Telescope, which went way over budget. So Habitable Worlds, as I understand it, is about a decade off, realistically. That's not probably what the timeline says right now, but that's what most space pundits think.
The next question is from Oculus, who would like to know if there is anything in space that we can't currently explain, or that we can't explain with current mathematics.
There are things we don't fully physically understand. Certainly, there are phenomena that we don't fully understand. We've just mentioned dark energy and dark matter. Those are the two classic ones. But it's not a deficiency of our mathematics necessarily, because our physical theories are pretty mature. So the laws of gravity and thermodynamics and how radiation works, and even hydrodynamics, the way gases work under high energy and high pressure, those are very mature theories, and they have a mathematical basis. So our mathematics is not the problem at the moment. It's a physical understanding, which also means that our observations are not sufficiently sharp or precise to pin down the nature of what we're observing.
The next question is from one of our online participants. Neha asks, what causes type 1a supernova events?
So type 1a supernovae are the ones that are in binary systems. Type 2 supernovae are single massive stars that explode as a supernova. So type 1a supernovae are a binary system where the mass transfer between the two stars gradually pushes one of the stars past the Chandrasekhar limit and collapses causes a supernova explosion, then a black hole formation. And because of the slow transfer of mass, it's a very well regulated event. And so essentially type 1a supernova go off with a very standard amount of luminosity. They're like standard bombs, which means in terms of their brightness, they're standard light bulbs. And that's why type 1a supernovae historically have been used to measure the distances to far off galaxies. And that's still a technique that works pretty well. So they're very important in astronomy because they're standard tools for measuring the universe on very large scales.
The next question is from Arif Roni, who asks, how do astrophysicists prioritize among exoplanets, so I guess observing exoplanets on Goldilocks zone, moons, and brown dwarfs for finding biomarkers? Well, I guess, how do they choose which biomarkers to look for? I guess that's what they're asking for. How do they prioritize that?
Right. So from the 7,000 plus exoplanets known, the first type of prioritization is to pick the nearest targets. From Kepler's work, most of the exoplanets found were hundreds or several thousand light years away. And that makes them very hard to do follow-up observations on. So they look for, among all the surveys and satellites that have been working to find exoplanets, they try and pick the planets that are close, by which I mean a few tens of light years. Then in terms of what biomarkers to look for, the ones they look for are the ones that we think have the biggest confidence of indicating biology, and that would be oxygen, ozone, methane, along with water vapor. And it's really a suite of biomarkers. There's no single biomarker that will convince, especially in noisy data, convince skeptical other scientists or a skeptical public that life has been detected. So biomarkers have to be measured in conjunction with a modeling of the planet based on its mass, size, temperature, and so on, so that we can show that the model has to have biology in it, photosynthesis, say, for microbes, to fully explain the spectrum.
Excellent. The next question is from one of our live participants. Terrence would like to know, do comets conceal full proteins? Could we find proteins out amongst the stars in comets? But then, I mean, we could extend this to other, clouds in space. How complex are the molecules that we find?
Right. So comets have been attributed, with complex molecules. The spectra of comets are complicated because molecules give complicated spectral signatures. But once you get to large molecules, it actually gets very difficult to tell what the spectral signature will be because it becomes ambiguous with other molecules, and there's so many features it's hard to measure them properly. So that's the observational problem. The expectation, however, is that it will be pretty unlikely to form large complex molecules. And so to put it simply, there's no evidence of proteins in a comet spectra. We visited some comets and asteroids, and again, by direct observation, we've not found any evidence of them. It's also pretty hard to know how they would form. So the most complex molecules that are found in any of these cool bodies, like a comet or an asteroid, are amino acids or complex molecules with perhaps a few dozen atoms. But as far as larger proteins, the kind that carry function and form in the modern biology sense, we haven't seen any such molecules.
Arif, who's on with us live, Arif Roni, has a question. We talked a little bit about different ideas that might emerge based on dark matter. And Arif would like to know specifically about MOND, or modified Newtonian dynamics. Is that is there any room for that with the sort of growing unknowns about dark matter and dark energy?
Yeah, MOND is, been around for a long time, and I guess the best way to put it is not quite dead yet. So MOND is modified Newtonian gravity. It became an explanation in the 70s and 80s as dark matter was indicated in all galaxies, that one way of getting around the need for dark matter was to modify the force law of Newtonian gravity, which is an inverse square law. So if you slightly modify the force law on large scales in the exponent, instead of being -2, you make it a slightly different number, you can actually get away from the need for dark matter at all. So obviously it's an interesting solution, because you're just tweaking the gravity law, not dramatically, but by a modest amount, and then you don't have to have this mysterious ingredient that we still haven't figured out what it is. But you pay a very heavy price, because if you alter the gravity law from strict inverse square law, you lose the conservation nature of the gravity law. And so you lose a very key symmetry argument in physics that makes gravity a self-consistent theory. So altering gravity that way is seen as being unnatural in physics terms. And then the question is it ruled out? Can we even rule out modified Newtonian gravity theories? And there's still an argument about that. Some claims have been made that MOND is ruled out, and there are still a few MOND proponents who say that's not the case. There are still some observations that can be better explained, or equally well explained by MOND as by a dark matter explanation. So I'd say it's a fringe view, a strong minority view in cosmology, but as long as we don't know what dark matter is and haven't identified that particle, assuming it's a particle, then MOND will continue, I think, to live on.
Excellent. Thank you very much. We are at the end of our session for today. For those of you who are around still with us, thank you for joining us. If you could hit the like button, that really helps our channel get the word out. The more people who like these live sessions, the more likely they are to be shown in people's feed for the next time. So that really helps us out. Make sure that you subscribe to our channel and hit the bell icon so that you get all of the announcements when we have future live sessions. That again will alert you when there is another one. And we'll take one last, I don't know, probably quick question here just to wrap things out, since I ended things abruptly. So we'll take this last question from SJ, who would like to know, is time travel possible according to Einstein's theory? And what is it that shows it is or isn't possible?
So Einstein's theory of special relativity, which is the one that deals with signal travel and synchronicity and coordinating clocks, and so how time is measured in the physical universe, Einstein's special relativity says that time travel is not possible, because in Einstein's special relativity, as any object approaches the speed of light, three things happen. The mass of that object increases, eventually exponentially, and so it resists further changes to its motion or acceleration. The time slows down in the reference frame of that object, and obviously the physical object also gets foreshortened, Lorentz contraction. All of those phenomena mathematically are built in such a way as to create the speed of light as an absolute limit. And in fact, the speed of light as an absolute was a premise of special relativity. So essentially, from the ground up, special relativity precludes time travel. That's a simple statement. So if time travel were possible, special relativity would be wrong in some important way. And we've really seen no sign that special relativity is wrong. More profoundly, if time travel was possible, then you have issues with causality, which is another foundational principle of how physics and the universe work. So most astronomers and physicists think time travel is simply not possible. It's not part of conventional physics. Thanks for all the questions, and Matthew for facilitating. And I don't remember if we have one more on the books, but we'll make sure we put the next few out.
Excellent. Yes, we have a little bit of a break to accommodate some upcoming travel for people on our team. So the next live session will be in 4 weeks, and that will be on Wednesday, October 23rd. So we have 4 weeks in between now and our next session. And if you join our listserv, so if you're getting class emails from Coursera, then you're set. If you'd like to join our listserv, you can scroll up to the top and join our Google listserv, or our Google group, really is what it is, and you'll receive announcements about live sessions, and we will get you'll get additional information about upcoming sessions. But that next one is October 23rd, and thank you again for joining us. We really enjoy seeing everyone. We hope that you all have a good rest of your week and weekend, and we will see you in 4 weeks. Take care, everyone.
Okay, bye. Are we clear, I presume?